Assalamualaikum. Hello and welcome to our video presentation Embedded Engineering Dynamics together with Ms. Suffeya Agao, and today we're looking at rigid body dynamics and the outline. We are first going to look at the equation of motion called for rigid body. Then we're going to discuss and how you can go about drawing the free body diagram of a rigid body, which is FBD. And then lastly, we will go through a few examples on how you can go about solving this rigid body motion problem. So let's start the math.
The solution of problem involving the motion of rigid bodies. In this equation of motion of a rigid body, we have the solving, the FBD process, the procedure, and the example. When we look at the equation of motion of a rigid body, there are two equations that are important. We have the transitional motion, which is in the x and the y direction, and those are the sum of all forces equals mass times acceleration, and here acceleration has got a subscript g, which means the acceleration of the center of mass. We also have the rotational motion, and here Newton's second law is written as the sum of all torques or couple moments around the center of gravity equals moment of inertia of the center of gravity times rotational acceleration alpha. To determine the steps that we need to follow to draw a free body diagram for a rigid body, so first we need to select coordinate system. The second one, identify the object. The third, draw all the external forces. Fourth, find the direction of all forces, and lastly, direction of acceleration. Now let's look at the example of the bloodhound supersonic car, and first we go and we draw the free body diagram including all the forces acting on it, and for that we need to understand some of those steps on this problem. And in this case, the x direction is to the left, so the car is moving to the left, so we can just assume that is positive x direction. The y direction is vertical upward, and positive rotation is clockwise. The step 2 involve isolating the vehicle from its surrounding, so we're going to draw just the outline of this car and ignore anything outside of it. Step 3, we have to involve the marking the applied forces and the reaction loadings, and unlike particle problems, these forces are applied at their actual location, and this is not necessarily the mass center, and it can be somewhere else on this object. Obviously, the exception is the object weight, which always acts to the center of the mass. And the step 4 and 5 are also the same when we consider particle free body diagram of all. Here is our free body diagram of the bloodhound. You can see clearly we have indicated our coordinate system with x to the left being positive y upward being positive, and we've got the positive couple moments in the clockwise direction. We've also indicated all the forces that acting on the bloodhound supersonic car. So we have thrust force of the engine being applied to the left. We have our weight of the car going through the center of mass pointing downwards, and then we have the two direction of forces on the wheels of the car, where we have got a reaction force of the front of the wheel of the car as well as the rear wheel of the car, and then at the bottom we just drew the kinetic diagram showing that the car is moving to the left. You will see here it's only a translational movement. There isn't any rotational movement in this case. So now that we've drawn the free body diagram, the next step would be to go and solve for all the unknowns, and this process is very similar to that for particle problem. we've just drawn the free body diagram, a kinetic diagram, and now we need to apply the Newton's second law to the free body and the kinetic diagrams included. And in rigid body dynamics, we need to use both the translational and the rotational motion equation. So let's just go back to our free body diagram. And now, the same as for particle problem, we have applied Newton's second law for both translation and rotation. Newton's second law. In vector forms of the sum of all forces equals m equals mass times acceleration, and this is our thrust force vector, our two reaction vector, and the weight of the car. We can break this equation into its component, and it's the x and the y component. And you can see for the x component we just have the thrust force and the positive x direction for the forces, and the y direction we have our two reaction forces at the front and the rear wheels, and they both got positive sign because they are upward, and we've denoted up as being positive. And then we have negative mg, which is the weight of the car acting downward and the negative y direction, and this equals to 0 as there is no movement happened. And the y direction, the only movement is on the x direction, so we can put this equation equals to 0. So now, for the rotation, the torques are being taken around the mass center. We've said that Newton's second law for rotation is the sum of all torques equals the moments of inertia around the center of gravity times rotational acceleration alpha. You can see here we consider the reaction force on the front wheel. First, we've got this torque arm of 4.75 meters, and we've got rotated this force around the center of gravity. It will be a clockwise motion, so our couple moment as a result of reaction force at the front wheel is a positive. As our convention is clockwise is positive, for the reaction force at the rear wheels again, you've got the moment are here of the 4.50 meters. And if we rotate this force around the center of gravity, it will be in an anti-clockwise motion, and that is why it's negative 4.15 times the reaction force at the rear wheels. The same goes for the thrust force. It is rotating in anti-clockwise manner around the center of gravity, and that is why it's got a negative unit here as well. Now, as before, we assume the jet force is 20% of the maximum. Hence, we give the thrust force a value of 18 kilonewtons, and the mass of the Blonde Hound supersonic car is 6,422 kilograms. So now we can start inputting the known values into the equation that we've got just created now. If we look all the forces in the x direction, it is just the thrust force equals ma, and we can quickly calculate the acceleration in the x direction as being meters per second squared. Now, when we consider the y direction, we can clearly see that there are two unknowns which we cannot solve for, and that is the reaction force at the front and the rear wheels. So we need a third equation to help us solve these two unknowns. We can use Newton's second law of the rotation, which we've been written down in the previous slide, and we can substitute the equation that we've got in the previous slide into this equation. And we got solved for the reaction force on the rear wheels as 32.13 kilonewtons. Now that we know the value of the reaction force at the rear wheels, the only unknown is the reaction force at the front wheel. So we can substitute the known value for the reaction force at the rear wheel and solve for the value of the reaction force at the front wheel, and we get a value of 30.87 kilonewton. So by using rigid body dynamics, we have to determine the three action force of the blunt hump as it from the rest accelerate, and we've also determined the acceleration. So now something that you just need to note is that the axis by which we applied Newton second law for rotation did not matter here since our rotation acceleration is equals to 0. So for the second example will be continued by Miss Suffeya Agao.
Assalamualaikum warahmatullahi ta'ala wa barakatuhu. My name is Suffeya Agao and here's the continuation of our topic. So example number 2, example of crate. If mass of the crate is 50 kg and the coefficient of friction between the crate and the surface is 0.2, determine whether it is likely to tip or slide and the acceleration for the case where P is equal to 600 newtons. So the first step is to first go and draw the free body diagram of this crate. And we can see here that we've indicated all the forces that we know of, and you can see that the normal force is acting on an arbitrary point O, which is an x on direction away from the center of gravity, and we don't know the value of x as this will ultimately influence if the block tips is over or it slides. Now, to determine if it slides or tips over, we need to first calculate the force to slide the case without tipping it over, and then we don't do the reverse to see which is smaller. So we can go and apply Newton's second law in the horizontal direction, which gives us the equation of the sum of forces equal M, and in this case, it is our external force P minus our frictional force. Now, for the scenario where the case is standing still and it's at the point of moving, the external force needs to be equal to the frictional force, and in this case, P needs to be greater than 98.1 newtons in order for the case slide forward and start moving. Now we can also look at the reverse scenario where we need to determine the value of P that will cause the case to tip over, and we can use Newton's second law for rotation about the center of gravity, which is the sum of all the torque forces equals 0. It is equal to 0 because there is no rotational acceleration for the scenario where the case steps over. The value of x needs to be at the point of the case and thus needs to have a value of 0.5 meters. So we can substitute the value of x of 0.5 meters and we can solve for the value of P, which in this case is 654 newtons, which is much greater than the applied force of 600 newtons, which means that the case will slide and not tip over. So now, we use the value of P for 600 newtons, which equation states it needs to be, and we calculate the acceleration at which this case will accelerate, and we add a value 10 meters per second squared. We can write this acceleration in the vector form, and because it's only on the x direction, it will only have an I component, and we can write the acceleration as equals 10I meters per second square. So for the summary of our report, we always need to first go and draw a FBD of the problem before we can solve it. And now we need to select a coordinate system indicating positive translational directions and positive rotational direction. Identify the object you wish to analyze and sketch its outline shape. Draw all external forces acting on the particle and couple moments acting on the object and label them. The direction of forces having unknown magnitudes can be assumed. The direction of the acceleration of the body's mass center, A, and alpha should be established on a kinetic diagram or in the coordinate axis. Draw a free body diagram following the steps outlined above. Apply Newton's law for translational and or rotational motion to solve for unknowns. So that's all for our topic. Shukran and wassalam.